Hello and welcome to this lecture series on microprocessor and microcontroller. And This is the 25th video, and we are going to start the final topic of this series, which is microcontroller, right? And there are many microcontrollers, but we are going to study 8051, right? So 8051 is a microcontroller. So what do I mean when I say that 8051 is a microcontroller? How is a microcontroller different from a microprocessor? So we have already seen its definition, but just to revise, microprocessor is just the brain part of the computer, right? However, microcontroller is a system on chip. That means you have the brain part as well as its peripheral. They all are fabricated onto a single integrated circuit. That's what we mean by microcontroller. So every microcontroller is a microcomputer. Microcomputer means brain and its peripherals. But the difference between microcomputer and microcontroller is that inside microcontrollers, it is essential that all of the peripherals and the brain has to be fabricated on the same chip. However, on microcomputer, brain part plus the peripherals could be fabricated on the same chip or on different chips. So both options are available, right? So microprocessor is only the brain part. Whenever we interface its peripherals together with itself to make it a complete digital organism, then in that case it becomes a microcomputer, right? So, however, microcontroller is already a microcomputer, and it's a special kind of microcomputer where all of its components and the brain part are fabricated onto the same single chip. So, one such example is 8051, and in this particular video lecture, we are going to study the architecture of 8051. So 8051 is no different as compared to 8085 microprocessor or 8086 microprocessor. The only point of difference will be in the execution speed, because whenever you are trying to fabricate all the components on the same chip, then the peripheral and the brain part, they will be communicating at a faster speed as compared to when you were connecting a microprocessor to its peripheral through wired connections, right? So you were making external connections. So those external connections are definitely slower as compared to when all the components are fabricated onto the same chip. So 8051 will be definitely faster as compared to 8085 and 8086. It primarily depends upon the operational frequency, which is different here, of course. But then the fastness is also partially attributed to fabrication of all the components on the same chip, because the communication between peripherals and the brain part, it is faster as compared to the situation in which those components were not on the same chip and they have been connected through soldered wires, right? So this is a general introduction to what microcontroller is and how is it different from a microprocessor and what is a microcomputer. Now, in this lecture, let us start with the architecture portion of 8051. So there are a lot many things to learn about the architecture. So we will take everything step by step. So let me begin with some important points about the architecture of 8051 microcontroller, right? So there are various points that we need to study. So we will study them through appropriate diagrams. And I have listed important points here for your ready reference. So let's begin with this point number one. So 8051 is a 40 pin DIP. DIP means dual inline pin package. What do I mean by dual inline pin package? So in your laboratories, you might have seen integrated circuits which are of rectangular size, and they have pins on one side and the other side, right? On the longer sides, they have pin. So those kind of integrated circuits are called as dual inline pin package. So 8051 is a 40 pin DIP, 20 pins on one side, 20 pins on other side, on a rectangular box kind of structure, right? So also this 8086 and 8085 are also the same. So 8051 is also a 40 pin DIP. The second point is it has it has a 8-bit CPU with registers A and B. Now again, this 8051 is having a 8-bit CPU, means it's again a 8-bit microcontroller, and it has registers A as accumulator, and it has got another general purpose register B. So it is usually involved with timer calculations, but whenever it is free, it can be used as good as A. So A is the accumulator register, and this is conventionally also true because in 8085 and 8086 we have also seen the utility of A, and A is responsible for holding the calculations or default calculation of many commands in 8051, right? So this also holds in 8051. Now, another important thing is another important thing is that it has got 16-bit program counter. So 8051 microcontroller has got a 16-bit program counter. So that means, if it has got 16 bits program counter, then the first address has to be 0000 in hexadecimal, and the last address has to be FFFF. That means you have got a 64 kilobyte memory onto which this program counter can operate, but that does not necessarily mean that it will have only 64 kilobyte of memory. We will talk about memory when we will reach to that section, but program counter is of 16 bits. So it can address a memory up to 64 kilobyte, but the memory attached to this 8051 microcontroller is little more than that, right? So we'll come to that point later. So similarly, it has got a 16-bit DPTR. Now, what is this DPTR? DPTR is data pointer, right? Similar to program counter, you have a data pointer. So in 8051, we need to keep in mind that program memory and data memory are separate. And to traverse the program memory, we have got this program counter. And to traverse the data memory, we have got data pointer, right? So the role that is played by program counter up till now in 8085 and 8086, the same role will be played by program counter here, but not for the entire memory, only for the section where we are going to write our code. And for the data memory, we are going to use data pointer. So the data pointer is also of 16 bits, right? So it can also address a memory location which can go up to 64 kilobytes, right? So after that, it has got a 8-bit program status word. We all know what program status word is. Program status word usually has bits which represent the status of operation inside the system at the current stage, and those bits are usually carry, parity, auxiliary carry, sign, zero, etc., as we have seen in 8085, and in 8086 there are additional bits for interrupt flag and so on and so forth, right? So program status word is also present here, and it is only of 8 bits, right? And then it has got a 8-bit stack pointer. So stack pointer is also there, and interestingly, you can see that this stack pointer is only of 8 bits, right? And this stack can be made anywhere inside your memory, so it's not a problem. So it is only of 8 bits. But the important point with stack pointer is whenever you make a system reset, so during the reset, every register, including program counter, DPTR, PSW, is reset to 0000H, or if it is a 8-bit register, 00H. But stack pointer will be reset to 07H after this reset hardware reset operation has been made, right? So the stack will start filling from 08, 09, and so on and so forth, because if the stack pointer points at 07H, then when you try to fill the stack, you know that it will get incremented. So stack pointer will be incremented. So the next location will be from 08 only, right? So this is one important point of difference when a reset operation is made. So on reset, the stack pointer is reset to 07H. Now let's talk about the memory. Let's talk about the memory. Now memory here is of two types. One is internal memory and another is external memory. Now, internal memory is the memory which is a part of micro controller, the 8051 microcontroller that we are using. So it's a part of 8051 microcontroller, right? And The external memory, it is not a part of microcontroller, but in case you want to improve the memory capacity of this 8051 microcontroller for some applications, you can definitely interface some memory to that, but it is not infinite in extent, it has got its limit, right? So coming to point number 7, internal ROM of size 4 kilobytes is present in 8051 microcontroller. So here we do not have just a single chip of memory which can be used as RAM or ROM. Here we have separate ROM and RAM sections for the internal memory. So internal ROM is present whose size is 4K bytes, right? So it is not that its maximum size is 4K bytes. Since it is already fabricated, so 4K byte, not more, not less. Internal ROM is available with 8051 microcontroller, and similarly internal RAM of size 128 bytes. Remember, it's not 128 kilobytes, it's just 128 bytes. So it is very small as compared to this 4K bytes. 4K is a huge number and 128 is very small number. So you have ROM which is huge in size, 4K bytes, and internal RAM of size 128 bytes. And the RAM here is not as simple as we have interfaced in 8085 and 8086. It is separated into different parts, right? So this RAM has got three different parts. So first part is it has got four register banks. What do I mean by register bank? A register bank, as you know, that bank is a place where we keep our money. So register bank is a bank which has a collection of registers. So one register bank has 8 registers, and you have four such register banks, right? So four register banks, each containing 8 registers. So in the in the RAM, that is random access memory or read-write memory, this demarcation is always there. That the initial part of your RAM will be occupied by register banks, which are four in number, and each register bank is going to have 8 registers. We are soon going to see it through diagram, so the things will become more clear to us. And then the next 16 bytes may be addressed at bit level. So there are 16 next bytes or 16 registers which are after these four register banks, and they can be addressed at a bit level. And the next 80 bytes which are used for general purpose data memory. So actually, without going through all of the slides, let me just show you quickly the structure of this RAM, because it is important to visualize it now. So here you can see it. You can see that you have got this bank 0, bank 1, bank 2, bank 3. So this is your RAM, random access memory, right? So this bank 0, it has got 8 registers. So you can see that addresses for bank 0, they begin from 00 to 07H. So it has got 8 registers of 1 byte each. Similarly, bank 1, bank 2, and bank 3. So all of these are here. After that, from 20H to 2FH, there are these 16 registers, and they are also of 1 byte each. So their addresses, you can see they begin from 20 and end at 2FH. But if you want to access individual bits, then you can see their addresses are also written here. For example, for 27H address, if you want to access this bit only, then 3B is the address. So when we will do programming, I will tell you how to access these individual bits of registers. So this is bit addressable location. So 16 registers are available, which are of 1 byte each, and each bit can be programmed separately to various programming instructions, right? After that, there are these 80 locations or 80 uh, 1 byte locations which are used for general purpose things. So this is the complete structure of random access memory. So if you to sum up all these locations, each bank has got 8 registers, and there are four such banks. So these are 32. Then 32 plus 16 will make it 48, and 16 plus 80, that is these general purpose regions, they will make it 128. So this is the complete RAM. However, in the same hardware, you have some special function registers which again occupy 128 locations, and they are also the part of the same hardware, right? But when we say RAM, we generally refer to this area, and this is 128 bytes. But we will see that this is also the portion of RAM. This is also the part of RAM where you have got 128 another bytes starting from 80H to 0FFH. out of which 21 registers that you see here, these 21 registers are used for some special purpose things. So these are special function registers, right? So they can also be addressed by bits or by their actual addresses, or in programming they can be addressed by their mnemonics also, or their names also. So that's what we are going to see. So if somebody asks you what is the RAM size of 8051, so you will definitely say 128 bytes. But 128 bytes only refer to this first section. Although this is also the part of RAM hardware, but then again, we do not say that it has got a 256 bytes of RAM. It's only 128 because these are special purpose registers and they are used for special functions. So you can't disturb them to keep general data, which is usually not done. And apart from 21 registers, the location which remains, they are hardly used for any purpose. So we do not count this as usable, right? For any general purpose. So this is what I mean by the RAM structure, right? So internal ROM is clear to us, which has a size of 4K bytes. Internal RAM is clear to us, which has a size of 128 bytes, not kilobytes, 128 bytes with this bifurcation as 4 register banks, 16 bytes which may be addressed at bit level, and 80 bytes of general purpose data memory. So this is RAM, right? In ROM, you will usually write your programs, and once a program is written to a microcontroller, for example, microcontrollers, they you can find them in your washing machines, your air conditioners, etc. So once a program is written to them, that hardware is attached to a bigger hardware, and it will be used forever for that purpose. So in ROM, we will write programs permanently. It will hardly happen that inside a microcontroller we will need to change the program. So we would prefer to write our programs in ROM. So ROM is also called as program memory in literature, and RAM is called as data memory because after reset, ROM does not get changed. However, RAM is reset to all zeros, right? Like these registers which we have discussed here, they all are reset to zero except stack pointer, which is reset to 07H. The RAM will be reset to all zeros. However, ROM will remain as it is because if a washing machine switches, if you switch off your washing machine and you start it again, it should function as desired. So the program should reside there. So ROM is not reset when the computer system is reset, right? So this is about the internal memory, and you can see that this 4K byte and 128 byte is very less for RAM and ROM. So there is a capability of extending it to 64 kilobytes. So 64 kilobytes additional external code or program memory, which is also called as ROM, can be connected. And similarly, 64 kilo additional bytes of external data memory or RAM can be connected, right? So internal memory is already there, but this part is optional. External memory can be connected or external memory cannot be connected. And the important point to note here is that whenever we connected the external memory with a microprocessor, as in the case of 8085 or 8086, we had this read and write signals which comes out of the microprocessor, and they were used to activate or deactivate that particular memory chip for reading or writing purposes. However, for ROM, that is for code or program memory or ROM, this read and write signal will not be applicable. Here inside microcontrollers, we have this signal which is called as PSEN, PSEN, which is called as program store enable. So this is applicable only for ROM or for code memory. Since from the ROM we will only be reading the code, so there is no need to write something onto ROM, right? And on that note, we do not use this read and write signal combined. We only use one program store enable. So this PSEN is used to read the programs from the ROM part, right? So this is also one point of differences which is applicable to the read and write signal. So we'll see this through diagrams also in a while. And code memory is selected by EA, 0 for internal, 1 for external. So there is a signal which is called as EA, or a pin which is called as EA. And if you make this EA pin as 0, that means external access. EA stands for external access. So if external access is 0, definitely the internal code memory or the internal ROM will be used. or if this EA is equal to 1, then the external ROM will be used. External ROM is of 64 kilobytes, as you can see here, and the internal ROM is of 4K bytes, which we know. So that's what I was saying when I was mentioning the size of this program counter and data pointer. It seems that since they are of 16 bits, so at max they can go for 64 kilobyte location, but here it is not the case. You can see that externally interfaced memories, whether they are ROM or RAM, they can be of 64 kilobytes, and the internally interfaced, sorry, the internal fabricated memories, they are already 4K and 128 bytes. So this program counter and DPTR, they need to have some mechanism of working with all of these memories simultaneously. So we will see through diagram how that is done, because we have more than 64K bytes of memory, and PC and DPTR, they can address memories up to only 64K bytes. So how that is done, we are going to see shortly. Then after that, talking about the peripherals which are already fabricated onto chip. So this 8051 microcontroller has got four numbers of 8-bit bidirectional ports, right? So ports, they, by port what we mean, anything that can take and give data. So it's a trans receiver of data, right? So it has got four ports which are 1 byte port, means each port is of 1 byte, and their names are from P0 to P3, P0, P1, P2, P3. And since each port is of 8 bytes, sorry, each port is of 8 bits, that is why you have 32 input output pins or 32 bits, right? So it has got these four ports. So port 0, port 1, port 2, and port 3 are their names. So now let us discuss what is the function of these ports. So you can see that all the ports are bidirectional. So all the ports, that is port 0, 1, 2, or 3, they are general purpose input output ports by default, right? So they are of 8 bits, read, write, both can be done. So they are all general purpose ports. So you can see it for port 0, port 1, port 2, and also for port 3. However, when you will see their pin diagram, you will also notice that with port 0, they have multiplexed the lower order byte of address and data bus, right? So as we have seen in 8085 and 8086, that address and data bus is multiplexed. So that multiplexed address and data bus is further multiplexed onto this particular port. So on port 0, there can be three things: the content of this port, or the lower byte of address, or the lower byte of data, right? So three things are multiplexed here. So we will see it through a particular diagram when we will study the pin diagram of this 8051. Similarly, port 1 is free. So port 1 is just a general purpose input output. So if you have to only use one port, prefer port 1, because it has only got one purpose. It has got no other multiplexed thing. However, port 2 is also a general purpose IO bidirectional port, but the higher order address byte is also multiplexed on this, right? Data bus is of only 8 bits. We have seen that this 8051 microprocessor is of, sorry, 8051 microcontroller is of 8 bits. So data bus will be of 8 bits. So those 8 bits have been covered in this port number 0. So for address bus, the lower byte and the higher byte will be present. So lower byte is there with port 0, and the higher byte will be there with port 2. So this is usually used to hold the higher order byte, which is multiplexed with this port 2, and this is used when external memory is to be used, right? And then port 3, it is a general purpose input output. So it is a general purpose input output port, and it is general purpose input output port in the case when we are not using any of the peripherals, because usually this port 3 is also associated with timer calculations, right? So we will see it when we will see the timing diagram, right? After that, let us come to the structure of timers that are present. So it has got two timers. This 8051 has got two 16-bit timer or counters, T0 and T1, right? And it has got a full duplex serial data transmitter and receiver, which is addressed to this S buff. So we will see this in the diagram, that full duplex serial data communication can also be done through this S buff pin. Then control registers are there, which are T control, T mod, S control, P control, then IP and IE. So we already know this IE and IP registers from our previous studies. Then it has got interrupts, and there are two external interrupts, three internal interrupts, sources, and in total 2 plus 3 plus 1, that just total 6 interrupts are there, including reset. So reset is also treated as an interrupt. So including reset, there are total 6 interrupts, out of which we have got 2 external interrupts and 3 internal interrupts. So when we will deal with the topic of interrupts in 8051, we will see what these interrupts are, and in this lecture probably we are going to see the structure of interrupt vector table also, right? So now let's talk about the oscillator. So it has got one on-chip oscillator of 12 megahertz. So it's a crystal oscillator whose frequency is 12 megahertz. So that is present there. However, you can also externally interface the crystals between XTEL1 and XTEL2 pins, and whatever externally interfaced crystal oscillator is there, its frequency is divided by a factor of 12, right? 12 megahertz. So it's divided by that. So as in the case of 8085 and 8086, also we have seen that whatever external crystal oscillator we apply, its frequency is usually divided. So here it is also the case. The frequency that you see here is also divided by 12. So this is a quick but general introduction to the 8051 microcontroller architecture in terms of important points. Now let us see these important points on diagrams, right? So now the things will become more clear to us. So let me start with the very first slide. So this is the general block diagram. So the architecture of this 8051 microcontroller will be studied through several diagrams, right? Because the architecture is too huge, so we need to first understand the broader parts, then we will see the details of each and every part one by one. So now this is the complete 8051 block diagram, and here you can note that all of that you are seeing here is just a part of the single chip. It's a part of the single chip. So it's not that the CPU is the chip and all these devices are interfaced to it. No, with this CPU, these all devices are fabricated onto the same chip to increase the speed, right? And the user should not bother about connecting these peripherals to the microprocessor, making appropriate connections and doing the appropriate programming. So already all these things are present. The user can directly purchase it and use it for his or her purposes, right? So we start with the CPU. We already know that it has got a 8-bit CPU because it's a 8-bit microprocessor. Then oscillator we have just talked about. It has got an internal oscillator whose frequency is 12 megahertz. You can also interface an external oscillator between XTEL1 and XTEL2 pins, and its frequency will be divided by 12 and then supplied inside the microprocessor, right? So uh, let's now talk about the RAM and ROM. So it has got a 4K byte internal ROM. We have also studied this, that it has got 4K byte of internal ROM and then 128 byte of RAM. And this RAM has its own structure, which I have just shown you. So it has got register banks, then some bit addressable memory, 16 such locations are there, 1 byte locations are there, and then 80 general purpose locations which are free for any purpose are a part of this RAM. So this RAM has got its own predefined structure. However, ROM has got no such predefined structure. Then there are two timers, timer number 0 and timer number 1, and the associated counter inputs are also there. Similarly, for interrupt control logic, you have got external interrupts which are 2 in number and internal interrupts which are 3 in number, and there is a reset interrupt. So total there are 6 interrupts. 5 are shown here and reset is also one of the interrupts. So it is also not shown here, right? Then you have got this bus control block which will be controlling the operation of address and data buses. Then you have got four input output ports, P1, P0, P1, P2, and P3, right? In out of which P0 and P2 are used for address slash data buses, right? So P0 is used for both address and data bus because address bus is of 16 bits, so lower order byte is used with P0, and data bus is of 8 bits, so the data bus is completely used with P0. However, with P2 you have got only the higher order address byte and the content of P2 itself. So on P0, three things are multiplexed. On P2, two things are multiplexed, and on P1, nothing is multiplexed. However, P3, as we will soon see, it is associated with some special signals used for control purposes. So it's also multiplexed thing, right? Then you have the serial control block where you can have this transmission and reception. So you can transmit one bit and you can receive one bit serially. So this is a general block diagram of 8051 microprocessor, and step by step we are going to study it in more depth, right? So we are going to elaborate on each block to be able to understand the complete architecture. So let me first give you a comparison of the 8051 family members, right? So 8051 is a microcontroller, and similar to it, there are other microcontrollers from the same Intel family, and they have got a similar architecture, right? So the numbers are shown here on the slides. You do not need to remember them, but you can see that they differ in their ROM and RAM sizes, right? So the size of ROM and RAM is different, and you can see that the number of timers that are available, they are also different. Then the sources of interrupts, you can see that the interrupt sources are also different. Somewhere they can go up to 9, and somewhere they're as low as 3. And IO pins, so most of them have got 32 IO pins. However, some of them have got 16 also. And there are some special features like WD stands for watchdog timer. So watchdog timer means you have set a timer for something, that this task should be completed up till this point of time. So this timer should give you an interrupt, or this timer should tell you in some way. So this watchdog feature is available in some of the micro controllers, and this analog comparator is also there. So analog computer comparator facility is also there, and an in service, in system programmable. In system programmable means that can you change the program of the ROM in runtime. So is that possible? So that facility is, I think, given by this microcontroller. So this is the 8051 family members. However, we are not going to study individually all of these because their programming languages are also a little bit different from each other, right? So I mean, one question that should automatically come to your mind is there can be many microprocessors and microcontrollers, and these days we also see that for mobile they are different, for computers they are different. One company has another kind of microprocessors and controllers. So are we supposed to learn the programming language or the assembly language for all of these? The answer is no, you don't have to do that. Fortunately, there are higher level programming languages like C and Python, where you can program in them, and through a special hardware which is called as compiler, or you can have assemblers also, your programs are converted into machine language. So you do not have to work with the assembly language to begin with. But if you have decided that you want to work with assembly language, then select one good controller or processor for yourself and learn the assembly language of that only and work with that. Because if you switch to another processor, then you have to learn another language, right? So to keep this compatibility, means to keep this programming language generic, we have higher programming languages which can be used, and whatever code you write there, it will remain same on every microprocessor, and through assembler and compiler it will be converted to the corresponding machine language which is suited to that microprocessor or controller, right? So this is one issue that needs to be addressed, but we should know at least one or two microprocessors or controllers and their assembly languages. Now, after that, this is again another picture of the same architecture, a little more elaborate. So you can see that there is this arithmetic and logic unit, and you have got this accumulator register and B register. Program status word is also there. Then program counter is there. Then your DPTR, which is data pointer, is there. So it has got its higher order byte, which is DPH, and DPL is the lower order byte. So this complete thing is your CPU, and then you have got this special function RAM. I mean, special function register was there in the RAM. So this is the special function register. You have also got ROM here. You already know what are the sizes of internal RAMs and ROMs. So nothing external is interfaced here. This is all internal to 8051. Then you have got port 0, 1, 2, and 3. They are all of 8-bit ports, and they have got their corresponding latches. right? Latches are necessary because you can see that most of them are multiplexed. So sometimes you want to latch that address or data to be used by the address or data bus, right? And similarly, you can see that this port one is completely free. And after that, you can see the structure of this RAM. It has got bank 0, 1, 2, 3, which have got 8 registers each, and 16 bytes, which are bit addressable, also are present here. Then you have got some extra memory, which is not shown here, of 80 bytes. And then there are these special function registers, which have got these uh, values, and we will study them one by one in this particular series of lectures. So there is this control unit also, which you can see that there is this EA pin, which is your enable external access. Then address latch enable. We already know the meaning of this from 8085 and 86. PSEN signal. It is used for ROM chips, right? To be able to read the data from ROM chips, and we have just discussed it. X, XTEL1 and XTEL2, they are used to connect the external crystal oscillator, whose frequency will be divided by 12 when used internally. Then there is this reset pin. VCC pin is for applying the battery, and you can use a plus 5 volt battery here. So plus 5 volt is the battery which is required for this microcontroller to operate. And then there is this ground pin, right? So this is a little more elaborate diagram of that. And let's move forward. So this is the pin diagram, right? So now the pin diagram will make more sense to us. So in this pin diagram, you can see that you have got this port 1. Port 1 is completely free. So port 1, it can be either accessed completely, that is bit number 0, 1, 2, 3, 4, 5, 6, and 7. They can be either accessed as 1 byte, or in programming, you can access only 1 bit of that also. So it is also possible. I mean, it is possible with every other port 0, port 1, port 2, and port 3. So you can access their individual bits, or you can access them as a complete byte also. So that is also possible there, right? So let's start with port number 0. So you can see that this port 0 is there, its 7 bits are there, and it is multiplexed with AD0 to AD7. So address and data bus both are present there. So three things are multiplexed: port's content, address bus, as well as data bus, right? After port 0, port 1 we have already seen. Now let's come to port number 2. So you can see that on port number 2, you only have this higher order address byte there. So it has got a 16-bit data, oh sorry, address bus. So the higher order byte is interfaced here, right? Then on this side you have got this psen signal. Psen signal is there, which is used for externally interfaced rom. So we will see it when we will try to interface an external rom here. Then there is this ale signal. Then there is this uh, enable the external access. So for that you have got this pin, and you can see that on port number 3, as I told you, that there are some control signals which are multiplexed with that. So you have got read, write, and then read and transmit. Then interrupt signals are there for timer 0, timer 1. Then this write and read is also there. This is not read and write, this is receive and transmit, RxD and TXT. So this is for serial communication, and this is for read and write. And this is for crystal oscillator, this is for ground. So now probably the pin diagram also makes sense to you, right? So this is the general pin diagram of that. And this is further elaborate diagram of the architecture, right? So now you can see again here you have got this accumulator, then B register, then temporary registers which are connected to ALU. So we have seen that this TMP2 and TMP1 registers in 8085 and 8086 also, where they were not directly accessible to the programmer, but they were used by this ALU for getting the data from various registers, right? So you have got this RAM, and for calculating the address, you have got RAM address register. So that is also present here. Then you have got port 0 latch, port 2 latch. So port 0 and port 2 are here. Then you have got EPROM. That means ROM chip is also present here. And you have got the ROM address register, right? So program address register means ROM address register. So this is associated with this thing. Then you have got this buffer here. Then PC incrementer, program counter is also there. Data pointer is also there. Port 3 and its latches are there. Port 1 and its latches are also there, right? So again, then you have got timing and control. So this P send, ALE, EN, reset signals are there. Oscillator is also there, right? So this is also another diagram for your architecture. So various authors they present it in various ways, and this is the special function registers format. So this is also presented here, right? So after this, let us see the program status word. So this is the format of program status word, which is fairly simple here. So you have got parity, then you have got this reserved bit. So this is not used for any purpose. Then you have got overflow. Then let's talk about this first. F0 is a user programmable bit. So user can define its own flag. So F0 is used for that. AC is for auxiliary carry and CY is for carry. So we are already aware of these things: carry, auxiliary carry, then parity, overflow, and F naught is user defined flag. Now let's talk about these two important bits, B3 and B4. RS0 and RS1 is their name. So what is the purpose of this? Now this is a very important, these two are very important pins. And you can see that if RS0 and RS1, there are two bits, so they can make four combinations. And if you select 00, then bank 0 will be selected, 01, then bank 1, bank 2, and bank 3 for 10 and 11 will be selected. Now, what is the advantage of this? Let me just show you that diagram first. So see, this bank 0, bank 1, bank 2, and bank 3, they are present in the initial stages of RAM. So they all contain 8 registers each, right? So when we used to write any function in 8085 or 8086, what we used to do was we used to put the content of program counter onto the stack. Then whatever important data was there in the program, for example, flag registers, etc., we also saved them onto stack. And if we want to save something else also, we can put them onto stack. And then we jump to that particular location and then we serve that program and then we come back. That's what we do, and then we retrieve the value that we have kept onto the stack and put it back into those registers. So this was a very time consuming process. So to get rid of that, we have constructed bank 0, bank 1, bank 2, and bank 3 here. And what happens in that, they have got 8 registers each. So normally this bank 0 will be used for calculations, right? However, if you want to make a switch to some other subroutine, then the parameters of that subroutine, where to jump, what to do, etc., it will be written in either bank 1, bank 2, or bank 3. So you do not have to save the contents of bank 0 onto the stack, right? You can just switch on to bank 2 and start executing your program from the parameters written over there. And when you want to return back, you just switch to bank 0. And how do you make that switch? It's very easy. In the program status word, you can see that there is this RS0 and RS1 bit, and this program status word can be changed by your programming instructions. So you can directly switch between bank 0, 1, 2, and 3, and these addresses can be used, right? So this is a very helpful thing. I mean, switching between programs is made fast by using this bank structure, right? So this is the status program status word, and all of the other things are very normal and already known to us. So I'm not elaborating on them. So I think this is more or less than it for this particular lecture. I will continue from here in the next lecture and we will further elaborate on the architecture, because the architecture of this microcontroller is fairly dedicated. So we need to spend one more lecture here. So thank you very much for watching this video. I will see you in the next video.